Hello! Recall that a NLP has the form minimize f of x subject to some gi of x is less than or equal to zeros, where f and gi's are any functions. In general, NLPs are difficult to solve. Here, we look at the case when f and gi's are convex functions. They have special nice properties that makes them slightly easier to solve. So what is a convex function? A function f mapping from Rn to R is convex if, for any 2 points a and b in Rn, and any lambda from 0 to 1, f of lambda a plus 1 minus lambda b is at most lambda f of a plus 1 minus lambda f of b. Essentially, this means that the graph of the function faces upwards. Here are some examples. Suppose we have f of x is equal to 1/4 x squared plus 2. We take a to be minus 2 and b to be 4, and here are f of a and f of b. The line segment between them represent a convex combination of f of a and f of b, which is the right-hand side of the inequality. If we take lambda to be a half, then the right-hand side will be the midpoint of this line segment. And the left-hand side of the inequality is just the value of the function. And the definition tells us that the function must be below the line segment. If this is true for all the points, then it is a convex function. We can look at something similar for this function in R2. We can take 2 points in the graph and look at the line joining them, and the function has to be below that line. We now give some examples of convex functions. Any even power with positive coefficient is convex. Any affine function is also convex. And any positive combinations of convex functions is also convex. And the key property that we will be using here is that if g of x is a convex function, then the feasible points of g of x less than or equal to 0 is a convex set. For example, if g of x is x squared minus 4, then this function is less than or equal to 0 when x is between minus 2 and 2. And this set is a convex set. The reason this is useful for us is that linear or affine functions are also convex functions. And we will replace any convex functions with an affine function. And we can apply LP techniques that you have learned in this course so far, which we know are easy to solve. And to help us turn a convex function into something linear, we will need the help of subgradients and supporting half spaces. We now define what a subgradient is. Suppose g is a convex function, and x bar is in the domain of g. Then, the vector s is a subgradient of g at x bar if g of x bar plus s transpose x minus x bar is at most g of x for all possible points x in Rn. This looks like a bizarre inequality, but the meaning of this is that if we treat the left-hand side of the inequality as a function, then it touches g of x bar. We substitute x equals to x bar in the inequality, and we see the left-hand side and the right-hand side are the same. And g of x is above this function. Take a look at this example of g of x equals 1/4 x squared plus 2, and x bar is equal to 2. You can check that s equals to 1 is a subgradient using the definition. The left-hand side is a function that gives us x plus 1. And the graph of x plus 1 looks like this. Notice that it touches the graph of g at x bar is equal to 2, and the graph of g is above this line here. We will note that in the special case of R1, s is the slope of the tangent line at that point. We now look at a second example, this time in R2. Suppose g of x is the absolute value of x1 plus the absolute value of x2 minus 2, and x bar is 2, 0. Notice that g of x bar is 0, so the definition of subgradient reduces to S transpose x minus x bar is at most g of x. You can check that s equals to 1, 0 is a subgradient, and we can calculate the left-hand side S transpose x minus x bar, which is this expression here, which is equal to x1 minus 2. We can illustrate this example here. This is what g of x looks like, and here is the point 2, 0. And this is the function that we just calculated, x1 minus 2. We see that it does touch g at the point 2, 0, and g is above this plane. We can do something similar with another subgradient, 1, 1/2. The left-hand side now gives us the expression x1 plus a half x2 minus 2. And this is what it looks like on the diagram. Now, subgradients are useful when we restrict the view to g of x less than or equal to 0. That is, for the feasible solutions of the NLP. We will get a supporting half space of the feasible region, and this is something linear that we can use to replace g of x. So what is a supporting half space? We let C be a convex set, and let F be any point satisfying S transpose x less than or equal to beta, which is a half space. Then, F is a supporting half space of C at a point x bar if C is a subset of F and S transpose x bar is equal to beta. We can look at this diagram here with a convex set C and a point x bar. And if we look at this half space here, we see that C is a subset of this half space, and x bar satisfies this half space with equality. It is at the boundary. We note that a supporting half space might not exist if C is not convex. In this small example here, there are no supporting half spaces for x bar. And the main theorem here is that we can get the supporting half space from the subgradient. Suppose that g is a convex function, and C consists of points where g of x is at most 0, meaning it is feasible for our NLP. If S is a subgradient of g at x bar, where g of x bar is 0, then the half space F, defined by S transpose x minus x bar is at most 0, is a supporting half space of C at x bar. We go back to our example of g of x and draw the feasible region of g of x less than or equal to 0. It is this diamond shape here. Our first subgradient is 1, 0, and the formula in the theorem gives us x1 minus 2 is less than or equal to 0. And we can draw this as this half space here. We see that it does touch the point x bar, which is 2, 0, and the entire diamond is contained in this half space. And note that the subgradient 1, 0 is now the normal vector of the half space. And we can do something similar for our second subgradient 1, 1/2. It gives us x1 minus a half x2 minus 2 is at most 0, and it can be drawn like this. And it is indeed a supporting half space. Now, normally, we need to use the definition to come up with the subgradients of a function at a point. But for differentiable functions, the task is much easier. If f is differentiable, then its gradient is a subgradient. And the gradient of f is a vector that can be obtained by taking partial differentiations of f with respect to x1, x2, all the way up to xn. And the gradient at x bar is simply replacing x by x bar in the gradient. We now look at this example of g of x is equal to minus 7x1 plus x2 squared minus 8. The feasible region of g of x less than or equal to 0 is drawn here. We now look at the point x bar, which is 4, 6. To get the gradient, we first differentiate f with respect to x1, meaning we are treating all the other variables as constants. In this case, we just get minus 7. We then differentiate f with respect to x2. In this case, x1 is a constant, and we get 2x2 as the result. So then the gradient at x bar can be obtained by replacing x2 by 6, which is minus 7, 12. This would be the normal vector of our supporting half space. And this is the half space that we will be using to replace our function g. We are now ready to optimize over convex NLPs. Have a look at this example here, where we are minimizing minus x1 minus x2 subject to 3 constraints consisting of convex functions. The intersection of these 3 constraints is our feasible region, which is drawn here. We now try to prove that 4, 6 is optimal for our NLP. First, we see that there are 2 tight constraints for our point x bar, which are 1 and 2. We will now replace each tight constraint with a supporting half space at x bar. For the first constraint, we get 8x1 minus 2x2 minus 20 is at most 0. And for our second constraint, our supporting half space is minus 7x1 plus 12x2 minus 44 is at most 0. And this shaded part here is the region of the intersection of the 2 half spaces. Notice that this region contains the feasible region of our NLP. We will now optimize over our shaded region using min minus 1 minus 1x as our objective. This is then equivalent to maximizing 1, 1x subject to the 2 supporting half spaces as our constraints. And now this is a linear program. So when is x bar optimal for our linear program? And this is the punchline we've been setting up for the entire video, and that is, it is optimal if the vector in the objective, 1, 1, is in the cone of tight constraints. We see that both constraints are tight for our point x bar, and there is indeed a positive combination of these 2 vectors to get 1, 1. So that implies that x bar is optimal over the shaded region. So it has the minimum value among all the points in the shaded region. But the shaded region contains the feasible region of the NLP, so x bar is also optimal for the feasible region of the NLP. We will now generalize this to the KKT theorem, which is a characterization of all the optimal solutions in convex NLPs. But for this theorem to work, we need something called a Slater point. X prime is a Slater point if gi of x prime is less than 0 for all I, meaning it satisfies all constraints with strict inequality. In our example above, we can see that 1, 1 is a Slater point. So the KKT theorem is as follows. Consider the NLP that is minimizing C transpose X subject to gi of x less than equals 0 for all I, where gi's are convex. We let x bar be a feasible solution. We also suppose that the gi's are differentiable and a Slater point exists. Then, x bar is optimal if and only if minus c is in the cone generated by the gradients of gi of x bar over all tight constraints gi. The backwards direction is illustrated in the example above, and the forward direction is much harder to prove, and we will not prove it here. We will now do the same example, except we will apply the KKT theorem directly. We are still trying to show that 4, 6 is optimal for the same NLP. The first step is to find a Slater point. This is generally a trial and error process. In our case, we have seen that 1, 1 is a Slater point, and we can verify that when you plug in 1, 1 into each of the constraints, the result is less than 0. Next, we will find the tight constraints for x bar. We substitute the values of x with x bar into the constraints to see which ones are equal to 0. In this case, we find that the first 2 constraints are tight and the third one is not tight. We then find the gradients for the tight constraints. The gradient of the first constraint is 2x1 and minus 2, and for x bar, we get 8 minus 2. The gradient for the second constraint is minus 7, 2x2, and for x bar, we get the gradient minus 7, 12. We then check if minus c, which is 1, 1, is in the cone. We solve the usual cone equation. 1, 1 is equal to lambda 1 times 8 minus 2 plus lambda 2 times minus 7, 12. Solving this gives us lambda 1 is equal to 7 over 41 and lambda 2 is 15 over 82. And since both lambdas are at least 0, 1, 1 is indeed in the cone. So by the KKT theorem, our x bar is optimal.